The ECHO ecosystem currently operates with a heavy reliance on its host engine. Building a complex game ecosystem directly on top of a third-party host creates a dangerous engineering trap. You tie your product's lifecycle directly to software you do not control. This diagram illustrates the problem. A massive cluster of ECHO modules are wired directly into a foundational Minecraft and NeoForge layer, fully dependent on its native registries. Furthermore, these modules are locked tightly to the host's event loops, unable to run without the NeoForge heartbeat. This direct coupling means any update or migration of the host engine ripples through the entire ECHO codebase, requiring cascading rewrites just to maintain basic functionality. For a live operational codebase, stopping production to execute a sudden ground-up rewrite is an impossible strategy. Prolonged downtime during a rewrite drains developer resources, breaks existing player saves, and risks the total collapse of the active project. To reach a standalone native platform, we must enforce a rigid logical boundary between the game systems and the host engine. We have to decouple the infrastructure without dismantling the existing product logic. That separation is the exact objective of the Phase 14 standalone runtime. The mechanism required to execute this transition safely is called dependency inversion. Instead of the high-level game code calling the low-level engine, we force the engine to adapt to the game's internal rules. We establish this inversion through a strict structural boundary called AdapterCore. The AdapterCore boundary intercepts every underlying engine assumption, every tick, every resource request, every network packet, before it ever reaches the core game modules. It takes those host-specific calls and reroutes them into internal engine-agnostic logic defined solely by ECHO. The AdapterCore functions as an active structural firewall. It protects the game from the host, ensuring the codebase survives engine changes intact. To enforce this firewall, we issue a strict architectural mandate. No shared ECHO modules are permitted to import Fabric or Forge APIs. We apply a secondary ban that prohibits any common server modules from depending on client-only UI rendering classes. Looking closely at this boundary, we start by identifying direct, hard-coded calls like Minecraft.getInstance and severing them entirely. Cutting these legacy links creates an immediate operational vacuum across the codebase. The modules suddenly have no way to communicate with the hardware or the game loop. We fill that vacuum using universal platform contracts. These internal contracts replicate the require functionality of the banned engine APIs, but they do so using ECHO's own internal logic. This structure allows AdapterCore to satisfy the exact feature requirements demanded by the pack readiness evaluator, proving the system is viable before it ever boots. Establishing this rigid contract layer isolates the core gameplay logic. Volatile engine mechanics remain trapped below the adapter, unable to break the higher-level code. A passive API wrapper simply renames a host function. Active structural translation fully converts data between two entirely different logical systems. To achieve that full conversion, the adapter layer relies on four specific internal subsystems. The first is the registry bridge. In this diagram, you can see a data packet drop from ECHO World Core into the routing interface, which formats it into a NeoForge-specific payload. This bridge takes standalone ECHO data definitions and safely maps them directly into NeoForge's required registries. Second is the resource bridge. Here, a texture request flows through the exact same routing interface down into the host system. The resource bridge ensures native ECHO asset pipelines, like textures and sounds, are reliably mapped to the host's specific resource pack mechanics. Third, we have the network bridge. This layer abstracts local client and server packet synchronization, laying the precise groundwork needed for future native multiplayer. Finally, there is the service bus. The service bus simulates the entire add-on lifecycle, loading modules and managing features, completely independently of the host engine's native load order. Without these four specific bridges, executing Ashfall on a decoupled codebase is impossible. The high-level systems simply have no pathway to reach the underlying hardware. With the adapter bridges defined, we enter Phase 12, the native CLI dry run protocol. The purpose of a dry run is to verify the new architecture by analyzing the dependency graph without ever launching a host NeoForge environment. We start by evaluating the module load plan within this isolated simulated environment. Then, we generate a simulated class path plan, proving the libraries resolve correctly. This generates specific diagnostic data. Here we see the side-by-side JSON outputs of the module load plan and the class path plan generated by the CLI. These outputs prove the AdapterCore successfully insulated the modules. By verifying the structural integrity at the diagnostic level, we prevent the catastrophic error of shipping a fatally flawed standalone runtime. That validated architecture enables the final transition to the Phase 14 standalone ECHO game runtime. Looking back at our architectural stack, this is the physical swap of the backend systems. The foundational NeoForge block slides horizontally out from underneath ECHO AdapterCore, and the standalone native engine block slides in. During this transition, we remove all NeoForge-specific adapter logic from the stack and activate the native standalone bridge. Look at the high-level game modules during this swap. They remain completely static. Zero code recompilation is required. Complex, high-level systems like world generation algorithms and entity data execute identically on the new backend. Uninterrupted execution of the exact same game logic on two incompatible engines is the strict definition of the dual runtime guarantee. In biology, a strangler fig vine creeps over and fully envelops a larger host tree. In software, this is the definitive pattern for legacy migration. We apply this exact pattern by having the AdapterCore implementation swallow the host engine dependencies layer by layer. Compared to a traditional software rewrite where everything breaks at once, this strategy provides immense risk mitigation. The game remains playable at every step. Once the new native runtime is fully proven, we execute the final architectural step of safely dropping the legacy host entirely. Evolving massive live codebases safely requires disciplined abstraction and rigid testing boundaries. They are the only viable methods to build the future without destroying the present.